Okay, so we're going to start by discussing ideal binary mixtures. And basically what we want to ask is, when we have two components that are distinct, right? So we have two distinct components. How does the free energy of the system change with composition? Okay. And in order to think about this, we're going to make an analogy with ideal gases. Okay. So we know for an ideal gas, if we have two things and we mix them, so we have two components, A and B, and we mix them, the pressure of the total system, since they're non-interacting, must just be given by the pressure of the A component plus the pressure of the B component, right? So if we take A gas and put it in a box, and we see how much pressure it is, and we take the B gas and we put it in a box and measure the pressure, and then if we then try to stuff both of them into the same box, the pressure should just be the sum of the two. And so we can write this as the partial pressure, and it should be related to the number of moles, as the partial pressure of A is just given by the mole fraction of A times the total pressure. Okay. Now we also know that in general, if we think about an increment of the Gibbs free energy, that's equal to V dP, right, minus S dt. So at constant T, right, we know that dG is just equal to V dP, right? And we know that we could obtain G by integrating, right, from some reference pressure, P0, to the P we want, V dP, right? And we did this in the case of the van der Waals gas. So for the ideal gas, if we do this, we get the integral from P0 to P of nRT over P dP. So we just get G at P0 plus nRT times the natural log of P over P0, right? So the free energy of the ideal gas just really depends on, well, it depends on the temperature and the number of moles, but it's related to the ratio of the pressures, right? So if we change the pressure, we change the free energy per mole, or we change the free energy and we hence change the free energy per mole. So now this reference pressure we can choose. So let's choose a reference pressure. And the typical choice is that we choose P0 to be something we call P theta, which is 1 bar. That's our typical reference pressure. And so if we want to think about G of the pure substance, so let's consider G of the pure substance. And we're going to denote that as G star. Okay. So in that case, G star is just going to be equal to the G at the reference pressure for that pure substance plus nRT times natural log of the pressure over the reference pressure. And similarly, we can write down a reference chemical potential, since that's just the free energy per mole, that would just be mu theta plus RT natural log of P over P theta. Okay. So now if we consider a mixture, since we have a sense of what the chemical potential should be for the pure substance, we can write down an idea of what G would be for the mixture. So G of the mixture is going to be equal to mu A times Na, right, we said, plus mu B times Nb, right? And so we can write that as Na times, and now we're going to put in the chemical potential of A. That's just going to be mu A in the reference configuration plus RT times the natural log of the partial pressure of A divided by the reference pressure. And then we're going to get a contribution from NB times the chemical potential of B, which will just be, or the reference chemical potential plus RT natural log PB over P theta. Okay. So now what we want to do is compare the free energy of the mixed gases to a container where each gas is held separately at the same pressure, right, where the pressure is PA plus PB, right? So we want to compare those two cases. One in which we're holding both gases at the reference pressure, and one in which we allow them to mix, right? So basically we're setting up an idea where we first start out with some pressure that we're exerting from the outside, but we're holding A and B separate, but they're both at this pressure, and then we're comparing it to the case where we are now holding the same total pressure, but A and B are mixed throughout the container, right? So here we have A and B, and here we have A and B together in the container. Okay, but the pressure, the size, the pressure on the box is the same in both cases. So we can calculate the difference there because we can write down an expression for the reference G. So the reference is going to be Na times mu A theta plus RT natural log P over P theta plus Nb mu B theta plus RT natural log P over P theta, right? And now if we take the difference between this reference G and the mixed G, so we figure out delta G of mixing. So this is the change in free energy due to mixing. That's equal to G of the mixed phase minus G of the reference, right? So that's just equal to Na, and now we can subtract this from the mixed, so that's just going to give us RT natural log PA over P, right? And then we're going to get plus NB RT natural log of PB over P. And now we can look at this and we can say, well, we know PA is certainly less than P. PB is certainly less than P because the total pressure that we're holding it at is equal to the sum of the two pressures, right? So these both must be small, so this has to be negative, and this has to be negative. So as a result, we can see that delta G of mixing must be less than 0. That is, So there must be a reduction in the free energy due to the mixing, right? And that delta G of mixing we can express as N RT times XA ln XA plus XB ln XB. Where the only thing I've done to get this expression is to just divide through by the total, or bring out in front the total number of moles times RT, and then use the fact that the partial pressure is related to the number of moles.